Welcome to Quantum Chemistry and Quantum Control. The module comes in two parts. The first one's really easy because you will be the end users of this. You will be using software and you need to understand how it works, but there will be no expectation of developer level research. The second part will be brutal, so quantum control theory and so on, where you will have to do some development because for some of you, your actual PhD project is about that stuff. Okay, so why do we want to model chemical systems inside a supercomputer? Well, the first thing they can be is in various ways unpleasant, for example, dangerous. That octanitrocubane is the strongest explosive known per unit volume. That is a nerve agent, that is a plutonium complex that's used for extracting plutonium from spent fuel rods, and you probably don't want to be near any of that, or at least the amount of paperwork that you have to fill to be near any of that will take a few months. They can, of course, be expensive. You can put molecules, for example, inside fullerene cages, and people here in Southampton do that. You can have natural products which are very hard to come by because they're secreted in the nanograms by their corresponding organisms. You can have something that's trivially just expensive because it contains platinum, but these are substances that we can only get by the milligram if we are lucky. Then, of course, there are chemical systems which nobody would allow you to conduct experiments on, and if you're working with mammals, birds, or God forbid primates, that's another pile of paperwork that you would have to do in order to be allowed to do that. And finally, a lot of chemical systems might not exist to begin with. They could be some exotic reaction intermediates which are just hypothetical. We think, well, that a little transition state might be there. How likely is that? In a lot of cases, we would want to bind and inactivate some enzyme, and we don't know what's going to bind, so we need to try a couple of million substances. If we are designing photovoltaic cells or looking at various exotic topological quasi-particles in magnetic materials, we would want to find out whether some eccentric electronic configuration is even possible to begin with before we commit what could easily be years of time to finding out experimentally. So the summary is we are doing things computationally because it's faster, cheaper, and in a few cases, funnily enough, a lot more accurate than it is to run experiments. And to give you an example of this kind of quantum mechanical modeling, this is something we've published a few months ago with Bruno Linklau, as a synthetic organic chemist here at the University of Ghent. He came and asked, well, which conformations of a particular fluorinated pentane have the lowest energy. So he was going to synthesize something, and he just needed to be assured that it's going to bend through complicated electrostatics in the way that he would like it to be. Well, what do we then solve? Mr. Schrödinger comes to our help. All of you have had this derived at various levels of sophistication to you. You all remember that momentum squared term, right? When the momentum becomes an operator, it is becoming a derivative for the electrons. Likewise, the momentum term for the nuclei. The interactions, the Coulomb interactions between the electron and the nucleus. So all of the fundamental constants here are not present because we use atomic units where, for example, electron mass and the elementary charge are both equal to 1, so we only have the charge number. Then the internuclear Coulomb repulsion and the inter-electron Coulomb repulsion, and you can see the sums over various particles here. Then we would have our total electronic wave function, and we would want to know the energy, and that, as you all know from your undergraduate courses, is an eigenfunction problem. So we've got electron momenta, nuclear momenta, we've got electron-nuclear attraction, and nuclear repulsion, electron repulsion, and finally, once we solve this giant eigensystem, we get the energy and the wave function. Now this kind of gives you an idea that this is going to be terribly complicated, particularly in situations where we have multiple particles, because these terms, for example, make this partial differential equation inseparable and therefore quite complicated. So for small molecules, we can do that in a matter of hours, and in fact in that particular case, and I'll show you how in a couple of lectures time, we have identified energy minimum conformations and just gave them back to chemists. They came back to us and said, well, what about all the intermediate conformations? And we had to scan an entire surface, so with respect to dihedral angles, so the angles that these various bonds make with each other in particular, and we saw a few population maxima at specific geometries, and then this is significant to synthetic organic chemists because they're designing their drugs with these conformational properties in mind. This is a fairly standard, simple calculation these days. No heavy elements in here. If we do get heavy elements like D and F elements, we do get relativistic effects. But for CH and OF, so first and second period elements, this these days is straightforward. And on it goes. We would want, for example, to find out what the salvation network is around a particular peptide in water, because we would like to know its effective hydrodynamic radius. This can be computed. We'd want to optimize drug binding to proteins. If we do know that a particular drug binds already, a reasonable question is, well, can we stick a methyl group here or there to make it bind a little bit better? The weaker the binding, of course, the more drug we have to give to the person. And so if we improve this binding affinity, then we can drop the amount that we are giving them, which would improve the toxicity response, for example, and in general just reduce the amount of the drug that is necessary. In catalysis, as chemists present here know, when a hydrogen molecule binds to the surface of platinum, the bond between the two hydrogen atoms is significantly weakened, and it therefore can participate in a variety of chemical reactions. The typical question would be which site in a particular solid that is coated or impregnated with a particular metal or material is the most appropriate for some catalytic transformation, and therefore which sites on these surfaces do we need to create more of in the design of a particular catalyst. Then, of course, certain types of calculations have become so sophisticated and they scale so well that it is possible, this has been done a few years ago on a large supercomputer, to actually have an atomic level three-dimensional model of a virus. You can see some nucleic acids being coiled up in there and the solvent surrounding, so these are very large scale calculations. And recent things like support for cryo-electron microscopy, modeling, for example, Alzheimer's disease fibrils. These are misfolded proteins which clump together, which we do need to model in order to be able to predict, for example, the drug binding sites on these things. So all of this leads to partial differential equations and numerical optimization problems, and all of this we will teach you how to model in this course, or at least where to begin, because this is a user level course that we don't go very deeply into the mathematics here. Another example here, this is an apparently incomplete map of human metabolic processes. So you can see we are fairly complicated beasts. And of course, every single one of these reactions is a differential equation and a partial differential equation if you are not lucky. So even in the case of linear kinetics, you do get an ODE, and a lot of this is nonlinear, so a giant system of millions of differential equations, and every single equation here, every single substance is an edge of a graph or a quantum process or a molecule whose energy and conformational properties and binding properties and solubility and electrostatics and magnetic properties and so on we would like to know. As you can plainly tell, it is quite impractical to actually measure all of this, or at the very least very expensive. Okay, so how do people do it at the simplest possible level? We will have a separate lecture on this, but in the extreme case we can simply just forget about quantum mechanics, ignore all the quantum effects, and say, well, okay, a molecule is just a collection of balls on springs. that do have some energy every time you move something around. So we would have some energy functional, which we assume to be the function of atomic positions. As you know from basic physics, the force is minus the gradient of the energy. Then, roughly speaking, Newton's second law, F equals ma for every particle present, and it is convenient in molecular dynamics because we need to use canonical variables from classical physics, not to use coordinates and velocity, but rather use coordinates and momenta. And then d momentum by dt is the force, and d coordinate by dt is momentum over mass. We will look in a few lectures' time at which solvers are used here, but after all of these solutions are done, we get trajectories for the positions and the velocities, and the typical time step is chosen to be sufficient to reproduce the fastest vibrations present. So, for example, CH vibrations, OH vibrations, and so on would have time scales in femtoseconds, and so a typical time step for these calculations is femtoseconds. And of course, the advantage of completely ignoring quantum effects is that we could run very quickly, right? This is substantially just Newton's equations of motion. We can predict statistical properties in a lot of cases, densities, melting points, vapor pressures, and so on. And of course, this is very easy to visualize because you simply plot coordinates and velocities of every atom and look at them with your pair of eyes. But of course, there are colossal disadvantages as well, because this is not quantum mechanical, then bond breaking cannot be described because it is a quantum mechanical process. Only these statistical properties, broad statistical properties, can be described, and anything that relies on quantum mechanics cannot, so notably all of the magnetic properties. Nonetheless, this is a very popular type of calculation, and a lot of the software packages that in particular the university has a site license for are there, and if you will end up folding some protein or looking at some binding candidates, this in a lot of cases is what you do. And how do you design that energy? Well, it actually usually just by the method of careful staring and guessing. We could put harmonic springs onto the bonds. Notice that this is just Hooke's law, right? So the force constant and then the displacement squared over 2. You could put similar quadratic restraints on the bond angles between two adjacent bonds. For dihedral angles, we could put some harmonic dependence because dihedral angles are floppy and can rotate around fully. We can put some short-range repulsion at the contact distance between the atoms so that they bounce when they come too close together. We can put van der Waals like 1 over r to the 6 attraction at short distances as well, and obviously there will be Coulomb electrostatics, etc. There are many terms that you could additionally add here. People even started training neural networks to replace this energy. In principle, all of these coefficients at least used to be extracted from accurate quantum mechanical simulations. So to some extent, this is an approximation of how the molecule behaves. But of course, you could stretch the bond to infinity here, and the energy will rise and rise and rise and rise. And of course, that is not physical. And so at some point, we have to move to quantum mechanics. But, well, this is useful. So look at the manuals of these two packages for more information about how that is done. That's an example from RIKEN, from the Quantitative Modeling Center in Japan. They modeled an entire cell. So this is cytoplasm, where the water has been removed and only the dissolved proteins visualized, as you can see, at a rather crude level. So what is shown here is small molecules are shown at atomic level, large molecules are shown with these lumpy plots, but you can see diffusion and conformational changes through the cytoplasm as that calculation proceeds. So if we completely ignore quantum mechanics, we can run plausibly accurate simulations, at least for some processes like diffusion here, on a cellular timescale. Okay, but of course this is not why we're here. We do need to take quantum mechanics into account. And so this brings us to the principal subject of this lecture course, that is quantum dynamics in the second half and electronic structure theory in the first half. So we will have to deal with the wave function, which, as you know, is a complex valued function, a solution of Schrödinger's equation, and it contains all information about our system, interestingly also about all of its past and all of its future. So many philosophical things about it, but very hard to calculate. You will all be using the university supercomputer at the point when you progress to the stage when you do your research. And a lot of effects like ionization, conjugation, hybridization, and a lot of quantum devices do require wave function level description in order for us to design them, in order to find out what it is that they are measuring, and to control them. So that's an example. If you take 6 phenyl rings and bind them together as a molecule by the fancy name of sexy phenyl, and this is one of its orbitals. And recently, using sophisticated electron scattering methods, it was actually measured. So the frontier orbital was mapped out experimentally, and this is a theoretical calculation. And you can see to within the accuracy of this measurement, more or less, this is spot on. That's another example. This is the orbital structure of the water molecule, where we do have 2 protons with their 1s orbitals, and we have an oxygen with 1s, 2s, and 2p. And these are the eigenfunctions of Schrödinger's equation that correspond to the various molecular orbitals in there, both bonding and non-bonding, and that is the sort of stuff that will interact, for example, in the gas phase, if we bump that molecule into something with sufficient energy. This has all become so accurate that synthetic organic chemists these days rarely even start doing synthesis unless they are completely certain that the calculation checks out and that they wouldn't be wasting valuable solvents and spectrometer time and so on for an unsuccessful attempt. Right, so let us go and look. Again, this is user level course. We are amateurs here. We are not developers of these methods. So I will only explain to you in broadest outlines what goes on in there. This is the equation that we have already discussed with all of the terms in it, comprising electron and nuclear dynamics, and that is the total wave function of the system. Firstly, what we do is we focus on just the electrons. Nuclei are much heavier, they move much slower, and in a lot of cases we only actually want the electronic structure, and so one of the first approximations we do, so-called Born-Oppenheimer approximation, is to assume that nuclei here are static point charges. So we only look at the electronic structure. Then this, as I've told you, is complicated and inseparable. So one of the ways of doing that, proposed initially by Hartree and then improved somewhat by Hartree-Fock, is to say, okay, let us consider the electrons one at a time and consider the dynamics of each electron in the effective total average potential of all the other electrons. So this is, of course, the momentum term. This is mv squared over 2. This is something we cannot ignore. But that is the potential energy term in a single particle Schrödinger's equation. And if we are lucky, we might be able to fudge something here so that the description is still plausibly accurate, even though effectively each electron is moving in the average electrostatic and exchange potential of all the other electrons. And this is called Hartree-Fock theory. As you can imagine, this is very approximate. In a real molecule, electrons will be dynamically avoiding each other, and so their trajectories would be correlated. In this case, every electron is effectively moving in the average field of everything else, but it's a starting point. And then in principle we can say, well, okay, why don't we start with some initial guess? We solve it for the dynamics of electron 1, 2, 3 and so on, or the corresponding orbitals, and then hopefully we obtain some self-consistent description in which from which we can extract at least those energies. But the trouble here, of course, as you can see from here, this is still an integral differential equation, which parametrically requires us to know the coordinates of every other particle in the system. So even though we decided to take this description, we need to shake it down a little bit before we can actually solve this in any way. In particular, computers are not very good at solving analytical equations, and we must translate it somehow into matrix vector numerics before we are able to solve this. So how do we do that? We need the concept of a basis set. This is our equation from the previous slide, and we will do the following. We will say, okay, we pick a set of functions. Usually these are atomic orbitals, the expressions for which we know, because for hydrogen-like atom, for example, they're even analytical. And we would say, well, okay, let us take our one electron orbital and say that this is a linear combination with some complex coefficients subject to normalization of some basis functions. And if we've chosen our basis well, this would be a fair approximation. What we can then do is we take this ansatz and we put it here on the left of the equation and on the right, and we rearrange the terms and see what is going to happen. So I've put that sum into there. That's the sum, that's the coefficient, and that's the operator acting on the basis function. Likewise, on the right, we have our energy of the particular orbital, and then simply this sum unchanged. What can we do here? Well, we can use some linear algebra. I will remind you what the function inner product is. If you take two functions and you have a metric Hilbert space, then their scalar product of f and g is the f complex conjugate, g straight, multiplied together, integrated over all continuous variables, and summed over all discrete variables, the so-called function inner product in a Hilbert space. Why don't we take this entire equation and calculate the scalar product of both sides with each of these basis functions in turn? So what is going to happen is we take that and we take an inner product with phi n. So phi n turns up here, and then the operator, and then the phi k. On this side, likewise, we take the inner product of this entire thing with phi n. So we've got this product here and that product there. So this is the result of this operator acting on this function, and then we take the integral, and that's just the integral. Now, the important thing about these is we fix the basis at the start of the calculation before we even began. And of course, these are therefore known functions, and these are known operators. And so this entire inner product, this entire integral, can be pre-computed for all k and all n. And you can see furthermore that this is quite parallel, because we can ask individual cores of a large computer to do those calculations for us independently. And then this is just the product of basis functions between themselves, and this basis set need not be orthonormal, because atomic orbitals, for example, in a molecule are not designed to be orthonormal, and so there will be overlaps and linear dependence potentially here. So this is called the overlap matrix, right? So it's index n and index k. So two indices, so the S, the matrix of all such numbers, is a matrix. And this is called the Fock matrix. Again, two indices, and we get the F and K out of it. Okay, but then what do we have? If we have a sum, then there's a matrix here over some elements of this C. That's a matrix vector product. And likewise here, if we contract the K index of S and K with the CK, that is the product of S matrix with the C vector. So we can rewrite it like this. We have matrix F times the vector of these coefficients, energy, the overlap matrix times the vector of these same coefficients. The F is called Fock matrix after Vladimir Fock, and this is the overlap matrix. And you can see a somewhat distorted eigenvector eigenvalue problem, right? You've seen this many times in your various undergraduate courses, except for the matrix S. But of course we can easily get rid of this. If we multiply both sides by S minus 1, then it would disappear from here and it would merge itself into the F matrix, and then this becomes a straight eigenvector eigenvalue problem, assuming that the S matrix is invertible, but that is easy to achieve if we choose these functions carefully. So suddenly, after a little bit of massaging and manipulation, what turned out to be possible is to translate an unpleasant system of integral differential equations into a straightforward matrix vector eigensystem problem. And thankfully software does this for you. You only need to understand this in general outlines these days. So this was the development, round about 1945, 1950. When these discussions were being held about how best to do that and which particular basis set to pick. You can see all of the particulars in Staba and Ostlund. It says modern, but the book is again from 1980s, but nothing much has changed since then, at least in the foundations of all of this. A particularly popular choice of basis sets is Gaussian functions. Now that is a very strange choice. In fact, when it was initially proposed, it ran into some opposition in that Francis Boyce was heavily criticized, in fact, in the 1950s for proposing them, but then they gradually became dominant. So why would he be criticized? Well, that's because Gaussians are rather remote from the kind of functions that you would actually see in molecular quantum mechanics. Normally, for example, the asymptotic behavior of molecular orbitals would be exponential, and Gaussian would plainly just decay too fast. And so if we take an atomic orbital, but we replace the radial part by a Gaussian, we get the usual spherical harmonics, which is responsible for SPDF and so on classification of your orbitals, and then the radial part. Why would this be in any way advantageous? The principal reason, firstly, is if you take a product of two Gaussians, then the result is another Gaussian at their center of gravity. So the product relationships of Gaussian functions are really simple. Secondly, a lot of integrals involving Gaussian functions are analytical. In fact, for non-relativistic quantum mechanics, all of them are. No matter how you differentiate it, no matter what you multiply it by, 1 over r, and so on, no matter how you combine it within the confines of that Schrödinger's equation that I've shown you, all of those integrals are analytical. And this was a decisive consideration in 1950s, because remember, the computer in 1950s was the lady downstairs, right? The vacuum valve devices have only just started to appear. So people had to work with kilobytes of memory, and so anything that could have been done analytically should have been done analytically. And secondly, the disadvantage, right, about not correctly reproducing the outskirts of the molecule might actually be an advantage, because they fall off very steeply with the distance, and so we can impose distance-based cutoffs on the various interactions and just hope for the best. But of course there are disadvantages. Again, Gaussian function falls off very steeply with distance. So incorrect asymptotic behavior, electron transfer, for example. A somewhat bigger problem that you will all encounter when you start computing magnetic properties such as J couplings is that the original eigenfunctions of Schrödinger's equation do have a singularity called a cusp at the nucleus. They make a sharp corner at the nucleus. But as you all know, Gaussians have smooth tops, and so around the nucleus, Gaussian basis sets misbehave and underestimate the electron density. And then, of course, in these basis sets at least, the Gaussians are centered at the corresponding nuclei, and so if you have something going on that doesn't involve nuclei, for example electron transfer, then the electrons would have to travel through areas of space that are not well covered by these functions, And so that is a problem. But still, at least originally, at least between 1950s and about early 2000s, so up to about 2001 to 2005, there was simply no other way to do computational chemistry on any reasonable hardware unless you use Gaussian basis sets. And people have since invented various mitigations. What we can do, for example, is take a linear combination of Gaussians, which approximates atomic orbitals somewhat better, and then we retain all of the advantages of using Gaussian basis set, but mitigate to some extent the disadvantages that I've just discussed. Okay, so what you will encounter when you start running software is abbreviations of this kind. This will occur multiple times in all of your practicals, and that is an abbreviation that describes an atomic basis set. Every atom in the second period or further does have electrons that do not participate in any chemistry. For example, for oxygen, this would be 1s electrons. For things like rubidium, this would be 1s, 2s, 2p, and so on. And that shell, chemically inactive shell, in this particular basis is described by 6 Gaussians. Then there's something called the zeta number, and this is the sets of Gaussians which describes the valence parts, and this is responsible for chemical bonding. And because bonding geometries, bonding environments, oxidation states can be quite flexible and varied, we need several sets of independent Gaussians which we would like to vary, and this is called a zeta number. So the number of sets of Gaussians that are independently varied in the basis set, usually 2 or 3, so this is a triple zeta basis. The first set of orbitals have 3 Gaussians, second has 1, the third has 1. G stands for Gaussian. And then there are 2 extra things which we must take into account. Firstly, the long-range behavior. For example, if you have a negatively charged ion, its electron shell is quite diffuse, and so we need to put a diffuse Gaussian in there to be able to describe those situations. And of course, in a lot of cases, the electronic structure would be electrostatically polarized, and we would need extra Gaussians equipped with higher angular momentum spherical harmonics to account for the left, right, forward, backward, up and down shift of electron density relative to the atom center. And so these are so-called polarization functions. I will not bore you with the detailed nomenclature here, that allow the wave function to become non-symmetric around the nucleus. So what you're looking for in those basis sets is firstly the zeta number, so that's the extent of valence shell flexibility, polarization functions, to what extent they can be polarized, diffuse functions, you don't need them, for example, for cations, but you do need them for anions. Sometimes extra super tight functions are added around the nucleus, and this is when you're dealing with the nuclear properties. Occasionally, special relativity is a pain for heavy elements like lead and gold, where people would just not look at what happens with the 1s orbitals, because this is strongly relativistic, and just stick an effective core potential in there, just an electrostatic surface that approximates in some effective way that inner shell. And then you've got Rydberg atoms, which are very highly excited states, very fragile, but that do require extremely high angular momentum numbers in the basis set and extremely diffuse functions, so you would have those. So the bigger the basis, obviously the better, because the better approximation it is going to have. The other class of basis sets that are very popular in electronic structure theory are these correlation consistent basis sets, which have their own completely different set of abbreviations. It says augmented, meaning diffuse functions, correlation consistent, meaning certain systematic improvement in energy as it gets better, polarized, polarization, valence triple zeta. So you've got triple zeta, so these two are roughly equivalent, in fact. But there's a giant database of all the atomic basis sets that have ever been designed for these things, which you can simply get those basis sets from, but a lot of software packages would just have some shipping with the package. I will not go through this. This is detailed description of everything that I've just talked to you about for sort of reference purposes. The rest you will find again in Szaba and Ostlund. I will only mention one other class of basis sets which is particularly useful. Firstly, in periodic solids, because it matches the periodicity, but secondly, in situations where the quality of the description of the electronic structure must for some reason be uniform everywhere in space. This includes, for example, electron transfer reactions. If we do not use Gaussians, but instead use complex exponentials, they're called plane waves. You can see instantly that this would lead to a different class of efficiencies compared to Gaussians. I've just told you that all of the integrals involving Gaussian basis functions are analytical, but in this case, a lot of the transformations, for example, differentiation, can be done analytically using Fourier transform. Right? You know that differentiation operation in time domain is equivalent to multiplication in the frequency domain, and so a lot of integral differential operators can therefore be applied by just forward Fourier transforming, multiplying, and backward Fourier transforming. But Fourier transform is very efficient. Its complexity is n log n in one dimension, where n is the number of points you are Fourier transforming, and so this therefore has its own efficiency tweaks and improvements. Plane waves are complex, and as a result, all electron integrals can be computed using fast Fourier transforms. So they're sort of analytical plus or minus a Fourier transform. They are periodic. If you're dealing with a crystal, that's perfect because you have periodic boundary conditions there anyway. They do not decay, so you have uniform description everywhere. They are already orthonormal by the definition of them, and so the overlap matrix is a unit matrix. Things become a bit simpler, and these waves are parameterized essentially by their frequency, and the frequency corresponds to energy, and you know how many of them you need because you usually vaguely know the energy scale of your process, and anything below those energies is interesting, and above you're probably not going to realistically access, and so simple accuracy criteria. But of course, a significant drawback is that these things are very, very smooth, and the nucleus is only a femtometer across, so 10 to the minus 15th meter. So these methods have significant difficulties around nuclei and for nuclear properties, but that has since more or less been solved in much the same way as it has been solved for Gaussians, but in a different way. Okay, so the final slide, I think this is to introduce the Hartree-Fock and the basis sets at the user level, is of course the variational principle tells us that for energy, the bigger the basis, the better, right? And as applied to quantum chemical calculations, essentially says if we have a class of functions which may be a solution to Schrödinger's equation, then the function that is nearest to the ground state solution is the one with the lowest energy. And the class of functions doesn't actually even matter all that much. You can take any basis set of any functions so long as they span your molecular orbital set. The lower the energy, the better the function. However, that applies only to the energy. The bigger basis set does not necessarily mean better calculation if you are dealing with something else. Something else could be, in this case, for example, the enthalpy, which includes vibrational contributions, could be chemical shielding in magnetic resonance, could be J coupling, could be polarizability. But as you can see, energy here systematically gets lower. This is the energy of a hydrogen atom, half a Hartree. Hartree is an atomic unit of energy. 3 Gaussians, 4 Gaussians, 5 Gaussians, 6 Gaussians. STO stands for Slater type orbitals, particular linear combinations of these Gaussians. The more you choose for the hydrogen atom, the lower the energy gets, and eventually in the limit of infinitely many you would have -1/2 exactly. However, if we look at the enthalpy in here and we start systematically increasing the basis sets, much bigger ones, and I don't remember enthalpy of what this was. This may be water in vacuum. So as we make the bases bigger and bigger and bigger and bigger, in fact the answer gets worse. So the experimental result is the straight line, and then for some reason it drops, and then it apparently approaches it, but actually if you keep increasing the basis set it would get worse again. So the important thing to bear in mind is this rule of thumb: the bigger the basis, the better the energy, only applies to the energy, and in a lot of cases only to the simplest systems. So when you are dealing with something else, certainly for magnetic properties, there is a giant amount of literature where people have tried every imaginable combination of the method and the basis set. They found out which ones work in which situations, and so for whatever property you are computing, your best bet is to dig through the literature to find out which particular method is best for your case and to use that method. Thankfully, these are all simply just parameters of standard software packages these days. You do not need to work through the nitty-gritty and the computer science of this. So I'll post a homework set tomorrow to the same site as all of this is at, where you are asked to do one of the simplest things you could do, is to take a molecule and to use Gaussian 16, which has a beautiful graphical user interface. You can just get all the molecules drawn in it by a mouse, and you will have to run the energy calculation using the Hartree-Fock method, and then to ask the program to calculate the volume of the solvent cavity around it when you put it into a polarizable continuum solvent. So this will introduce you to basic molecular orbitals, to basic electrostatics, and to basic energy calculations using this Hartree-Fock method. And we will leave it there. We will not go into the details of the numerical implementations of that, at least for now. All right, that's me. Any questions?